What if I told you there's a ship the size of a city that can operate for 25 years without a single drop of fuel? That sounds impossible, but it's real and it's been used for decades. So how does it actually work? A Nimitz-class aircraft carrier consumes approximately 300 megawatts of electrical power at cruising speed. 300 megawatts? That means nothing on its own. So picture this. It is the electricity supply for a large regional city of 700,000 people, entirely around the clock. And that power is generated by 2 reactors the size of a small room. Now, a second number. Fuel. The exact quantity of uranium in the reactor core is classified. The US Navy has never disclosed it, but one thing is known. The entire core fits inside a reactor the size of a small room, and it is enough for 25 years of continuous operation. For comparison, a conventional oil-fired carrier, like the British HMS Eagle of the 1960s, consumed up to 1,000 tons of fuel oil per day at full speed. 1,000 tons every day. That is 3 railway tanker cars every 72 hours. A nuclear reactor eliminates that logistics chain entirely, but to understand how, you first need to dismantle one very common misconception. Most people assume a nuclear reactor is something like an extraordinarily powerful explosion in slow motion. That uranium simply burns, just very, very efficiently. At first glance, that sounds plausible. We know atomic bombs use uranium. Chernobyl used uranium. The logic seems obvious. The reactor burns, only slowly. But here is the problem. Nothing actually burns. The physical process is fundamentally different. In a car engine, fuel reacts with oxygen. In a reactor, there is no oxygen, and none is needed. A nucleus of uranium-235 absorbs a single neutron and splits into 2 smaller nuclei, roughly krypton and barium, plus 2 or 3 new neutrons, and an enormous quantity of thermal energy. Those neutrons strike further nuclei. That is a chain reaction. What is really happening is not combustion, it is a difference in mass. The fission products of uranium weigh slightly less than the original nucleus. That difference, literally a billionth of a gram per single fission event, is converted into energy by Einstein's equation, E equals mc squared. And since c is the speed of light, squaring it produces a colossal multiplier. 1 kilogram of uranium, fully fissioned, releases as much energy as 2.5 million kilograms of coal, 2.5 million to 1. That is where the 25 years come from. The simplest explanation is this. The reactor heats water, the water spins a turbine. The turbine generates electricity, much like a thermal power station, except that instead of gas or coal, nuclear fission provides the heat. That is true, but it is only the surface layer. It still does not answer the central question: why does the fuel last so long? The reactor on Nimitz-class carriers is the A4W, jointly developed by Bettis Atomic Power Laboratory and Knowles Atomic Power Laboratory, and built by Westinghouse Electric Company. It is a pressurized water reactor, a PWR, operating on a 2-loop system. The first loop is the reactor loop. Water under pressure of roughly 150 atmospheres circulates through the core, where fission takes place. The pressure is so high that the water does not boil even at 320 degrees Celsius. It simply heats up and transfers that heat onward. The second loop is the steam loop. Through a heat exchanger, the heat is transferred to water in the second loop. That water does boil, converting to steam, and the steam drives the turbines, both the propeller shafts and the generators. The entire ship is powered by this flow. It is worth pausing on a detail that few people know. The fuel in a naval reactor is not standard uranium oxide, as used in civilian power plants. It is a metallic alloy of uranium and zirconium. It does not crack under the vibration of a ship's hull, and withstands marine conditions that would cause a land-based assembly to fail within months. The reactor does not consume all its uranium at once. Control rods made of boron or hafnium are inserted between the fuel elements. They absorb neutrons, slowing the reaction. The operator controls the depth to which these rods are inserted, and thereby controls the power output. This is nothing like a gas burner knob. It is far more precise. The reaction responds within seconds, but the rods move gradually, and the balance is maintained continuously. Each A4W reactor produces 550 megawatts of thermal power. Two reactors together provide 1,100 megawatts of heat. Approximately 190 megawatts of mechanical power is delivered to 4 propeller shafts, enough to drive 100,000 tons of steel to more than 30 knots. But here is where it becomes genuinely interesting. Most people think fuel either burns or it does not. In reality, fuel degrades in a very specific way, and that is what determines the service life. The fuel assemblies contain highly enriched uranium-235 at a concentration of 93 to 97%, known as HEU. Civilian reactors of the VIVER type use 3 to 5%. The difference is fundamental. High concentration means the reaction proceeds efficiently with a smaller quantity of uranium. That is why the reactor is so compact. But there is a second mechanism that almost no one has considered. The reactor does not die when the uranium-235 runs out. A portion of uranium-238 present in the assembly in far greater quantities is converted under neutron bombardment into plutonium-239. Plutonium-239 is also fissile. The reactor generates new fuel in the course of its own operation, not in the quantity it consumes, but this contribution meaningfully extends its service life. It is like an engine that partially synthesizes its own fuel while running. And there is a third mechanism, the one most responsible for those 25 years. It is called a burnable poison. That sounds like an oxymoron, and it is. Fresh fuel is too reactive. Give it full freedom from the start, and the reaction is unstable, burning through the fuel in the first few years. So neutron-absorbing materials, gadolinium or boron, are built directly into the fuel assemblies. They artificially suppress the reaction at the beginning, then they gradually burn away themselves under neutron bombardment, in step with the uranium as it depletes. The poison disappears at precisely the moment the fuel begins to weaken. Reactivity stays stable across the entire service life. It is like a spring with a built-in brake that releases itself at exactly the right moment. Now the physics that protect the entire system from catastrophe. Neutrons released during fission travel very fast, but uranium-235 nuclei absorb slow neutrons far more effectively. So, between the fuel elements, there is water. It slows the neutrons and increases the efficiency of the reaction. But more importantly, if cooling is lost, the water disappears. The moderator is gone, and the reaction slows on its own. A pressurized water reactor has a built-in negative feedback mechanism. The physics itself protects the system, and here is something no one expects. A carrier's reactor cannot simply be switched off at night and restarted in the morning. When a reactor shuts down, one of the fission products, xenon-135, continues accumulating for several hours afterward. It absorbs neutrons more effectively than any other element in the periodic table, and if enough has accumulated, the reactor will not restart at all. A land-based power station simply waits 24 hours for the xenon to decay, but an aircraft carrier in the open ocean cannot wait a day without propulsion, so the reactor is designed with sufficient excess reactivity to overcome xenon buildup and restart at any moment. Had they used standard enrichment levels, 3 to 5% as in civilian plants, the reactor would need to be refueled every 3 to 4 years. The carrier would enter dry dock for 18 months, 5 or 6 times across its service life. Each visit meant billions of dollars and months of lost combat readiness. The choice of highly enriched uranium is not a technical compromise, it is a strategic decision. The two-loop reactor system is like a thermos inside a saucepan. The radioactive water of the primary loop never contacts the turbines. If something goes wrong in the primary loop, the secondary remains clean. Radioactive contamination of the steam turbines would mean stopping the ship and exposing the crew to radiation hazard. The control rods are like brakes on a bicycle. You do not stop the wheel entirely. You regulate the speed, pull the rods out fully, and the reaction reaches maximum power, insert them fully, and the reaction shuts down. Between those two extremes lies the entire power range of the ship, from dead slow to 30 knots. In 1964, Task Force 1, USS Enterprise, together with the nuclear cruiser Long Beach and the nuclear destroyer Bainbridge, circumnavigated the globe in 65 days without a single refueling stop. 30,565 nautical miles on nuclear propulsion. A conventional carrier of the same class would have required roughly 20 port calls. Each stop meant logistics, security, time, money, and tactical vulnerability. Now it is clear how this works physically, but why does any of it matter? Why such complexity, such secrecy, such cost? The answer is simple and vast in its implications. A nuclear carrier can remain at sea indefinitely. The only constraint is food and ammunition for the crew. This means the ship can transit from Norfolk to the Persian Gulf in 3 days, without stops, without logistical windows, without escort tankers that are themselves targets. During the Cold War, American strategists worked out a straightforward calculation. A conventional carrier can be neutralized by cutting off its fuel supply routes. A nuclear carrier cannot. It simply goes where it needs to go. Yes, the reactor costs more upfront, but over 25 years, the absence of fuel oil, escort tankers, and the entire logistical infrastructure more than recovers that difference. And finally, the cost of failure. If the negative feedback does not engage, if the reactor loses cooling and does not shut itself down, the result is not an explosion. A reactor physically cannot explode like a bomb, and that is important to understand, but it can melt down. That would create a radiation emergency aboard the ship. That is precisely why the safety systems are redundantly duplicated 5 or 6 times over. Everyone involved understood where physics does not accept apologies. And now a question that is rarely asked aloud. What happens if an aircraft carrier is struck and a missile or torpedo hits the reactor compartment directly? The reactor will not explode like a bomb. That is physically impossible in this design. But the explosion from a missile can rupture the cooling loops. If cooling is lost suddenly and the emergency systems do not respond in time, the core begins to melt. Radioactive fission products enter the water and the air. For crew members nearby, a lethal dose can arrive within minutes. For the surrounding ocean, contamination can last for years. That is why reactor compartments are positioned deep inside the hull, below the waterline, surrounded by multiple layers of armor and buffer compartments. A damaged carrier can be repaired. A radiation emergency at sea means the loss of the ship, the crew, and the surrounding waters for decades. The Navy understands this, which is why reactor protection is priority number 1, ahead of weapons and ahead of the flight deck,